Hi guys. In the last video, we stopped at symmetries of a group, symmetries of a rectangle, a group of symmetries of a rectangle, and what we found was there are 8 symmetries, right? There are 8 symmetries, and the symmetries are, the symmetries are as follows. The symmetries are part of a group which will note as G. We will denote as G. And that includes the action that does nothing, the rotation by anticlockwise rotation by 90 degrees, double rotation, which is rotation by 180 degrees, rotation by 270 degrees, a rotation followed by the vertical flip, a 180-degree rotation followed by the vertical flip, a 270-degree rotation followed by the vertical flip. Tell me if I've missed out anything. Oh, the vertical flip. Yeah. So these are the 8 elements, 8 actions of the 8 actions or symmetries of the group of a rectangle, right? Okay. Now we come to this particular problem. As seen above, the elements of a group acts on the objects that is a rectangle with its corners numbered 1 to 4. If instead of at a one rectangle, the elements would act on each and every element of set X, we have a set of X objects, and G is said to be acting on X. Fine. Let us consider this set X, which is denoted by these are the 7 elements of this set. I'll just move this. Yeah, these are the elements of the set, and as you can see, A has this is a rectangle divided into 4 sub-rectangles. A has all the rectangles white. B has the rectangles along the left diagonal blue, and those along the right diagonal white. C has the rectangles along the right diagonal blue and the left diagonal white. D has the top 2 rectangles blue and the bottom 2 white. E has the left 2 white and the right 2 blue. F has the the top 2 white and the bottom 2 blue, and G has the left 2 white, blue and the right 2 white. Okay, so these are the 7 elements of group A, of set X. Okay, we choose any one configuration. We choose any one configuration, say B. And we ask what other states are reachable from B using the actions of G. Okay. So what are the actions on G? Under the new set of actions we defined, E, R, R square, R cube, RF, R squared F, R cubed F, and F, where F is the or vertical flip. Sorry. F হচ্ছে the vertical flip, or we can actually use the horizontal flip too. That will also create the same group. So let's just call it the horizontal flip instead of the vertical flip. Horizontal flip, and R is the anti-clockwise rotation by 90 degrees. So we choose an element B and we do what it says out here, right? What does it say? We will take each and every action of G, apply that action to B. Let's see what happens. So B acted upon by E will lead to B because E does nothing. B acted upon by R. So R is what? A rotation by 90 or by 90 degrees in the anti-clockwise direction. So this blue comes down here. This white would come here. So that we get C. Right? Next, B followed by R square, or the double rotation is basically applying R to C. So this blue comes here, and this blue comes here, this white comes here. So that gives us B. That gives us B. Next, what about the triple rotation? That'll be just applying R to B, right? Because double rotation, you apply R once, you are going to C, apply it R twice, you come back to B. So triple rotation is just applying R to B again. So again, we get C. Okay, now the flip, right? The horizontal flip. The horizontal flip is what? It is rotation about the vertical axis. So if you reflection around the vertical axis. So if you reflect around the vertical axis, this blue comes here and this blue comes here. So what we get is a blue here and a blue here, a blue on the top right and a blue at the bottom left. And that's nothing but C again. That's nothing but C again. Okay. What if we apply B? What if we apply a rotation followed by the flip to B? Applying the rotation to B, we get C. And then applying the flip to C. Let's see what happens when we apply the flip to C. This blue will come here. This blue will come here. So we get a blue here and a blue here. And that's nothing but B. What happens if we apply R square F to B, which is a double rotation? What does a double rotation to B take us to? It takes us to B. So this is basically applying the flip to B, and that gives us C. Okay. Now the triple rotation followed by the flip. The triple rotation applied on B takes us to C. So we just applied this flip to C. If we apply the flip to C, we get B. So to answer the question asked here, what are the elements of the set X that leads from B as a result of the actions of the group G? And we can see the only elements that result are B and C. So B and C are the only, the B and C are the only elements of X that result from G. And here it says the answer to the first question, which is this question, is the orbit. So B and C is basically the orbit of B. And if you study a little further, or if you experiment a little further, we'll realize that it is also the orbit of C, because all the elements of G, when acting upon C, will take it to B and C, to the same set BC. So BC is the orbit of B and the orbit of C. Okay, the next question we ask is, what elements of A act on B but don't take it to any other state? That is, it fixes B. In other words, what are the elements of B, elements of G, which do not take B to the only state other than B which B leads to is C. So here we have to just find out the elements, the actions which do lead to B itself. So E is 1, R square is 1, RF is 1, and R cube F is 1. So this set is going to be E, R square, RF, and R cube F. So this is called the stabilizer of B. This is called the stabilizer of B. And if we study a little further, we will realize it's also the stabilizer of C. One more thing. What is the order of the orbit of B? The order, what is the order of a set? The order of a set is the number of elements in the set. It's plain and simple. So the order of the orbit of B is 2. And the order of the orbit of C is also 2, because both are the same set of order of length 2. What is the stabilizer? What is the length of the stabilizer of B? How many elements does the set stabilizer of B contain? It contains 4 elements. So the stabilizer of B has 4 elements, and the stabilizer of C, being the same set, will also have 4 elements. Right? Right. Okay. This is exactly what we just discussed. It's just written down in a more organized manner. Let G be the set of symmetries of X. So these are the symmetries. We now try to find the orbits and stabilizers of X. We take the configuration A, and we apply all the actions of the group G on A. And we will see that the only element that it leads to is A, because there is no color here. All the colors are of all the 4 subrectangles are white. So whichever way you turn it or rotate it or flip it, it will lead to A only. So the orbit of A is A. And the stabilizer of A is all the elements of the group, because all of them lead to A. So stabilizer of A is the whole group. Next. We just did our demonstration with B, so this will be easy to see. As we could see, the B, when acted upon by R, it went to C, and when acted upon by R square, it goes back to B. When acted upon by R cube, again it comes to C. Similarly, when it is flipped, it goes to C, and double flipped, it goes back to B. So the only elements that B would lead to is C and B, And the only elements which C would lead to is also B and C. So B and C is the orbit of B and the orbit of C. And thus the stabilizer of B is also the stabilizer of C, which is this set, which we just found out. Acha, this is a little interesting. What are the orbits of D? Okay, we have to find the orbit of D, right? We enlist the elements of group G as, again, R, R square, R cube, flip, R flip, R square flip, R cube, flip. Okay. So D is the thing in question. You apply R. You apply R to D. This is D. You apply R to D. What is R? R is just rotating by 90 degrees. Oops, not in this, not in the clockwise direction, in the anti-clockwise direction. So these two blues will come here, and it would lead to configuration E. So it comes to E. R squared would be a further rotation by 90 in the clockwise and the anti-clockwise direction, and it leads to F. R cube would lead to a further rotation anti-clockwise by 90, and that would lead to G. That would lead to G. Then we do the flip. We do the flip on D. The flip on D, because it's a horizontal flip, and both sides, the left and the right, are identical, it leads to D. The flip leads to D. It doesn't change the configuration, right? So next, R flip, rotation followed by the flip. Well, D, R applied on D takes it to E. So we just apply the flip on E. If we apply the flip on E, as we can see, it goes to G. Next, R square flip. So R applied on D goes to E. Again, another R applied on E goes to F. So R squared applied on D goes to F. Now apply the flip. If you apply the flip on F, the left and right are the same, so it stays at D. And last but not the least, R cube flip. So R cube takes it to G, and the flip on G would lead to E. That is all. We have exhausted the elements of the group G. So, oh, and one more thing we need to list as well, and that is the identity element of G, which does nothing. It keeps D at D. Now, so we can enlist these outcomes in a set called the orbit of D. So the orbit of D will contain D, E, F, and G, because those are the elements that result from D due to the actions of G. And if we study it a little more, we'll realize that the orbit of E is also the same set, which is D, E, F, G. So is orbit of F, and so is the orbit of G. And now the next thing we have to figure out is What are the elements of G which keep D at D? So this is one, E is EE, which is a F keeps D at D, F, R squared F keeps D at D, but then oh, sorry, I made a mistake here. This is not, this will not be D, this will be F. This will be F, because R squared takes D to F, and then you apply the flip on F, you stay at F. So this will be F. So R square F does not come under the stabilizer. So this is out. So these are the only two elements which come in the stabilizer of D. And that is what is listed here. Similarly, we can find out the stabilizer of E, the stabilizer of F, and the stabilizer of G. Okay. What we observe is when the orbit of D, when the orbit is the whole group of length 8, the stabilizer is of length 1, as we saw. The orbit is of length 1, the stabilizer is the whole group of length 8. When the orbit is of length 4, the stabilizers are of length 2. So the orbit is of length 4, the stabilizer is of length 2. When the orbit is of length 2, the stabilizers are of length 4. The orbit is of length 2, the stabilizer are of length 4. So this basically, the relation we are getting is that the orbit length multiplied by the stabilizer length gives us the length of the group. And that is nothing but the orbit stabilizer theorem in group theory. So our problem will be solved using the orbit stabilizer theorem. We'll be proving the Burnside lemma using this orbit stabilizer theorem. And then using the Burnside lemma, we'll be solving the problem we have, which is trying to color a 64 square chessboard using 5 different colors.